Hello everyone, I'm Sean Richardson, graduate student in computer science at Georgia Tech. This is a summary of an incredible paper presented in 2024 at the IEEE Symposium in Oakland. The paper is titled Volttack, Control Internet of Things Devices by Manipulating Power Supply Voltage. Now, I'll give upfront credit to the authors listed on this title slide. My presentation is merely a summary of their excellent work. The outline of this presentation will include an overview of the Volttack paper, problem statement about why the vulnerabilities exist, background on IoT devices, a model of the threat scenario, how power supplies affect electronic components, how this attack can control sensors and actuators, how this attack was evaluated in the real world, a discussion of exacerbating factors and recommended mitigations, acknowledgement of related work, and a conclusion. First, an overview of the Volttack paper itself. The paper starts with an introduction to Volttack as an attack on the power supplies of IoT devices. It then discusses a variety of attacks with varying frequency and amplitude of input signals to affect sensors and actuators. Then it validates those attacks against a variety of common IoT devices and with realistic attack emplacement methodologies and devices. On the right, you can see a basic diagram showing that the attack can be from a variety of malicious power sources, including batteries or coupling devices. The manipulated input signal impacts downstream sensors and actuators. Manipulated actuators could cause damage and harm in industrial processes to both hardware assembly and operator personnel. And manipulated sensors could report erroneous measurements like incorrect braking force commands that lead to a car crash. Finally, the paper gives detailed ideas in its call for improved power supply security for various ways to cheaply and effectively try to mitigate these types of attacks. The problem statement. IoT devices rely on stable power supplies. The designers of the functional part of the IoT device generally expect that the power supply has been designed so that if its output is, say, a 5-volt rail or a 12-volt rail, that those rails are at about 5 volts or 12 volts within a certain tolerance that's plenty good for the rest of the device to work as expected. However, these assumptions might not be valid, especially in the presence of something like a Volttack injection. To motivate the listener about some of the impact possible with this attack, I'll give you 4 examples here cited by the authors of the paper. The DYTB002 force sensor was found to be vulnerable to a mere 1 volt inject at 342 megahertz precisely. And upon receiving that signal, the output can be that the sensed force is cut in half. And if this force sensor were on the brake pedal of a vehicle, for example, then as the driver is trying to avoid a wreck and presses the brake pedal at what they know to be a normal force to them, the car reading half of that intended force due to this attack could end up resulting in a doubling of the brake distance of the car itself and a car crash, causing injury or potentially death. Secondly, the DHT11 temperature sensor, a very common environmental sensor for things like temperature and humidity, was found to be vulnerable to a mere half volt injected at 121 megahertz. And that such an attack could cause the output sensed temperature to read 139 degrees Celsius high. If this temperature sensor were, for example, used in a vat at a factory when the factory was trying to heat or cool a certain content of that vat, like dye, then reading 139 degrees high could result in erroneous cooling commands, and you could end up in an unstable temperature situation which at a British dye factory actually resulted in an explosion of the dye vat. And that can certainly cause damage, injury, or death. Thirdly, a Futaba S9602 servo was found to be vulnerable to a 1.3 volt signal at 314 megahertz. And that with that signal injected, the servo could rotate a robotic arm, for example, over 58 degrees erroneously. And that could cause production to cease at a factory. That could cause damage to surrounding equipment or the thing being manufactured. And if a human operator is nearby, a 58-degree swing of a robotic arm could cause injury or death as well. Fourth, the Volttack 05 valve, upon receiving a mere half volt at 75 megahertz, could open erroneously by 34%. If this valve is supposed to be closed and now opens 34%, and it's used in something like a gas line, that could cause a gas leak, which certainly can result in an explosion, and again, injury or death, damage, things like that. Existing protections in IoT devices, which are namely various types of voltage regulators, often fail to block high-frequency signals, and that's due to the physics of electronic components and the fact that the designers have to make certain trade-offs with cost, available space, choices of which components are going to be available, and how those components are arranged and the types chosen to target specific frequencies. Generally, designers will target mitigating lower frequencies that are associated with noise, and we'll see later in the presentation that's often below about 80 megahertz. And the trade-off is often that the designers are not attempting to mitigate higher frequencies because they don't expect those higher frequencies to be present. But you can see in the middle of the slide, if those higher frequencies are injected maliciously, then that could cause problems. And unfortunately, while the modern world is moving toward further miniaturization of IoT devices, which has many benefits certainly, with lower power requirements, smaller size to fit in more places, maybe do more things with available space. The side effect of that is that components are closer together, which can drive unintended coupling of the physics of those components. And with less space available inside of IoT devices, the designers may have to make choices to remove certain components that might do a better job of power regulation. And all of that together can mean that this miniaturization for consumer benefit or factory benefit, etc., is actually driving vulnerability for these types of attacks. Some background on IoT devices. The main components of an IoT device include power supplies, sensors, and actuators. Power supplies themselves are actually fairly complicated, though once they're designed, like I mentioned earlier, they're often an afterthought as the rest of the device is designed. Within a power supply itself, depending on whether the IoT device overall is a higher power device or a lower power device, it may draw from AC current for those high power applications or direct from DC current for lower power applications. That will then dictate how many converters there are within it. So AC to DC converter to go from alternating current to direct current, and then to step down to additional separate direct currents, potentially down to 12 volt and a 5 volt, for example, with DC to DC converters. Those are often called switching regulators, where there are components that are switching power on and off rapidly, pumping that through a capacitor to try to smooth out that signal. The end result is still a little bit variable, and so that's often put through a low dropout regulator, which dissipates any remaining ripples as heat and doesn't involve any switching itself. The final output of all of that is usually a very, very smooth signal, despite a original power source that might have had a lot of variability. However, like mentioned previously, there are often assumptions about the frequency of input signals that all those various passive and active components need to regulate into that smooth output signal. The power supply rejection ratio is the ability to reject input noise and result in a smooth output. So high PSRR is desirable for that greater rejection of input noise. It is critical for the rest of the IoT device to function correctly, since the actuator and sensor portions of the device are expecting very smooth power. For example, that flat 12 volts or flat 5 volts. But because the components themselves are actual physical devices, they, at certain frequencies, they don't always behave per the typical model for those devices, and may not be blocking higher frequency malicious signals. This scenario we're talking about with the threat is that there's an individual, an attacker, who is attempting to manipulate sensors or actuators through the power supply. And they'll do so via these high frequency signals to bypass the power supply's intended protections. And that can result in superimposed signals on the real input signal, or changing the input to output transfer function. Thought of differently, that's changing the gain from the input to the output, so the multiplier of input to output signal. It does require physical access to the IoT device and or modification of the IoT device itself, which certainly presents a challenge to the attacker, but you'll see in a moment, definitely not an insurmountable challenge. And interestingly, after that physical access and the emplacement of the attack device, if the attacker chooses to include something like a Wi-Fi module with their in-place device, then they no longer need to be physically present to actually trigger the attack. They could simply send a command over Wi-Fi, over Bluetooth, some other remote means, to command their device to go ahead and commence the attack. How does input power affect electronic components? Fluctuations in input power can interfere with both passive and active components. The input frequency has varying effect on the input to output signal gain, or ratio of input to output. We can see that on the right side here with a couple examples of voltage regulators that are failing to attenuate input fluctuations at higher frequencies. The x-axis is frequency, low frequency on the left, high frequency on the right, and gain, being the ratio of output over input, is shown in the vertical axis. The green arrows are pointing at cases where as frequency is swept from lower frequencies, which are expected noise regimes, up through higher frequencies where the designers aren't expecting input frequencies to occur. We can see that certain components within these complicated voltage regulators end up exhibiting unexpected qualities, and the gain actually goes above 0 dB, which in this case means that the output fluctuations are actually bigger than the input fluctuations, the exact opposite of what we would want with attenuating input fluctuations. The device on the top, we see one major peak there at about 110 megahertz, and in the bottom device we see a handful of peaks starting at about 230 megahertz and occurring again in the 300s and 400s. Back on the left side, the high frequency inputs then, as you can see, can bypass these filters, these voltage regulators, and that can also have downstream effects on other components. That's shown in the lower left. This is just an example of a certain transistor and the relationship between its input voltage and its output current. Buried within this equation, we see a lowercase f pointed to by the middle green arrow, and that is the input frequency. If that input frequency for this particular transistor were to go very high, then the small fraction that that's a part of goes lower, and with the denominator of that larger fraction decreasing, then the overall fraction increases, and we have a higher gain from the input voltage to the output current. So again, that's in this case higher frequency for this transistor can result in higher gain to the output. How do we control sensors and actuators with this attack? We've shown that high frequency inputs can bypass intended input regulation. This figure shows one particular example of a regulator design using negative feedback. That feedback loop naturally has a delay, and if we inject a high frequency malicious input, shown as the leftmost green in this figure, at just the right frequency, we can take advantage of that loop delay as a phase shift and mitigate some of the intended feedback attenuation of the input signal. That could then allow the input signal to propagate to the output on the right, and we reach our next question of, if let's say the input signal is higher frequency at 200 megahertz maybe, how is it that downstream components expecting control signals at perhaps 20 kilohertz would be able to read that malicious input signal that's many orders of magnitude higher frequency? Well, the answer is that some of those downstream components may be sampling for control inputs at much lower frequencies, and due to aliasing, our malicious signal can then be down converted inadvertently by these components into their actual control signal frequency. So the power supply output fluctuations can thus end up altering the downstream components, being sensors or actuators. Servo motors and valves are particularly vulnerable to this type of attack because their control inputs are fluctuating signals themselves, and as opposed to devices that maybe take a binary on or off input. So if our malicious input is a fluctuating signal, it's much easier to superimpose that on expected fluctuating control signals. And various demonstrations of Volttack that you'll see in a moment have shown that you can actually achieve very predictable impacts on sensors and actuators. It's not that these fluctuations end up in unpredictable or uncontrollable results. In many cases, they're quite controllable and predictable and repeatable. That's been a lot of theory about this attack, but does it actually work in real life? It sure does. The authors of this paper evaluated it thoroughly, demonstrating it on 6 different sensors and 3 different actuators, spanning things like force sensors, environmental sensors for temperature and humidity, servos for robotic arms, and electric valves. Further, one might ask, could there actually be a realistic vector to get this malicious signal into power supplies of real systems? And the authors explored and demonstrated 3 different attack vectors that span a variety of scenarios and are very realistic for things like disgruntled employees, somebody gaining unauthorized access to a facility or device, or simply approaching an exposed IoT device out in the world. First off, a counterfeit battery. If you see the black battery case on the left, if somebody were to simply open up that case, pull out the normal battery materials, the anode and cathode metal and such, replace it with a smaller version of that to free up space inside, and then populate the rest of the inside with a Volttack signal generator, maybe a remote triggerable Wi-Fi module, and then the additional circuitry to down convert voltages and combine it with the battery's voltage. Then repackage the battery. They could simply swap out a legitimate battery for this manipulated battery and carry out the attack. Secondly, a current injection probe is taking a wire and physically connecting it from the Volttack to the IoT device at the desired inject point. This can help make sure that the Volttack signal is very precisely delivered to the IoT device. One disadvantage, though, is it could leave the Volttack malicious device susceptible to damage in higher power applications if we're tapping into a high power AC line, for example. Thirdly, they demonstrated a customized coupler, which is taking advantage of the fact that as current passes through a wire, it induces an electromagnetic field around the wire. If that wire is placed parallel to another wire, the electromagnetic field impinges on that other wire and induces a current within it. So, without physically connecting wires from the Volttack device to the IoT device, the malicious signal can be injected into the IoT device. A disadvantage is that the conversion to and from the electromagnetic field can result in some attenuation of the malicious signal and degradation of the attack itself. But an advantage is that the Volttack device not being directly connected via a wire to the IoT device would not be as susceptible to power fluctuations from the device itself and associated damage. Lastly, the authors showed that after testing a variety of devices across various times of day and that had varying manufacturer tolerances and such, that variability did not actually block the ability to have predictable manipulations of the IoT devices. It did drive a little bit of standard deviation in some of the results. For example, a servo motor might be more or less than 58 degrees beyond where it was supposed to be, but they could still fairly predictably control where that servo was. A discussion on what we might do to mitigate this attack. We've shown that IoT devices are broadly vulnerable to Volttack, and that further miniaturization of IoT devices can increase their vulnerability. Designers often rely on electromagnetic compatibility or EMC testing to make sure that their devices are not susceptible to expected noise. However, that noise testing is typically at lower frequencies than what we might maliciously inject to get around the intended voltage regulation. So, one mitigation would be to expand the frequency range of electromagnetic compatibility testing. And that would allow designers to catch earlier on in the design phase that they are susceptible to these higher frequency Volttack attacks. As to what they might do to mitigate such vulnerability once discovered in EMC testing, there are a couple main paths that are fairly cost effective depending on the IoT application itself and the expense of the device itself, barring these protections. One of them is to enhance the PSRR, the power supply rejection ratio, with enhanced noise rejection. And that can be done for as little as about $2 per IoT device, and that's for additional circuitry components. That can block the incoming attacks. However, if incoming attacks get through, a designer may want to take the additional step of also having real-time voltage monitoring, which can be done for about $1 per device. And what this could do is alert an operator or alert some smart functionality of this IoT device that there were unexpected fluctuations coming through, and it could shut down this device or tell other downstream devices to no longer trust or place less trust in the outputs of that particular IoT device. Lastly, the authors wanted to acknowledge related work and ensure that the reader understood Volttack in the context of that related work. Others' prior attack work has often focused on digital circuits in a wide variety of devices, whereas Volttack focused on analog circuits in IoT devices specifically. Others' prior attack work often looked at directly injecting signals to cause faults in digital logic circuits and or impact the way that software processed the inputs on board that device. Whereas Volttack sidestep the need to perform an attack on the firmware and instead attack the power supply before the firmware. Others' prior attack work often focused on electromagnetic interference by placing malicious devices in proximity to IoT devices to cause intended effects, whereas Volttack focused on indirectly injecting the signal in the power supply so that it had downstream effects throughout the actual device. In conclusion, Volttack shows that there are critical vulnerabilities in a wide variety of power supplies in IoT devices. Manipulation of those power supplies can have significant negative impact on sensors and actuator behavior in IoT devices. Current defenses, like filters and EMC tests, are often insufficient to block these attacks. And future IoT design must prioritize the security of power supplies if these attacks are going to be mitigated. So designers need to take this seriously. It is feasible and relatively cheap to design better defenses and test that those defenses are adequate. And if this is all taken seriously by designers, consumers, other buyers of these devices, then these attacks can be mitigated and we can avoid the potential damage and injury and loss of life that could result from these attacks. Thank you.